For me, if it doesn't happen this week, it's over. So you'll have to get a new member.
That might not be a bad thing.
And she's on sabbatical, I'm on sabbatical, doesn't happen this week, which it won't. So you gotta get 2 new members.
Okay, so I'll try to see if we can make it.
And guess what? There's a whole bunch of faculty members coming back from sabbatical. They just have a big old target on their bags that say, sign them up. Alright? I think you're like my 8th or 9th. So, you know what?
Morning, guys.
Morning. So, Fan has been evacuated to the basement for a tornado drill. You can't call in for a little bit, but Rich is missing, and you were missing, and she was missing, so.
Oh, I was actually not
No,
that
you were
bad.
missing. You were on Route 1.
I didn't know they have tornadoes in Detroit.
I don't get it either.
So when did that happen? Just a few minutes ago?
Yeah, we talked to him like 5 minutes ago. He said he was just evacuated out of the building. Yeah.
Like
It's,
security guards come
15
to
to 20 minutes usually takes in these situations.
not out of the building, to the basement.
To the basement,
Yeah,
I'm
going
sorry.
out of the
True.
building in an actual tornado would be bad. We saw what happened with Dorothy.
You saw?
Yeah, it's the 1950s, Wizard of Oz, right? Come on, guys. Black and white. Different culture, right?
I did have to worry about tornadoes going up. 15-20 minutes.
Well, it's already.
I think we'll probably get started then.
What do we do with Rich?
Oh, Rich.
Rich isn't here either. There's some accident for the southbound people on Route 1. We could just call him in, and you know what? We pretend we call him in. Or Skype him in.
What did did you talk to him? What did he say?
Yesterday I sent him a reminder email.
See if I can reach him.
Do you have slides for tonight?
Yeah, Rich Martin just pulled in.
Alright. Now Marco's trying to call him, but alright, that's perfect.
I just saw him.
Alright, that's great.
I present you. So I graduate.
My name is Ted. Sorry.
So you work on security, how do we know you really are Gorkem? I've never seen proof of your actual identity.
True, but you see me, actually you know me for 5 years with the name of Gorkem, so either I have a really nice planned backup story, or
But you sure look like you've aged a lot in this 5 years. Has it been that grueling?
getting mature is...
It took a long time to answer. So you said this is the parking lot, you should be here any minute.
Yeah, no problem.
Okay, sorry. All right.
have it.
A little bit.
Yeah, I have some.
Alright, fantastic. And Van said he'll just call when he is allowed out of the basement.
All right, we're here for Gorkem's thesis defense. I think Gorkem needs no introduction here. He's been around for a while and you all know him. Yeah, please get started.
Okay.
Do you want to leave the light on? Or?
Yes. Thank you very much and welcome to my presenting. The title of my talk is the Enhancing Vehicle Data Availability and Privacy for Connected Cars. Yes. Let me start with the connected vehicle systems. With the evolution of technology, more vehicles become connected every day, like personal cars, buses, trains. Do I block you by the way? I'm sorry. Or actually, if you like, you can go there because I will be using it. So if I, sorry about it. With the evolution of technology, more vehicles become connected every day. Personal cars, buses, trains, and planes are just a few of them. With the recent technologies of the connected vehicles, and actually one of them is called dedicated short-range communication or DSRC systems. The location information, acceleration, steering wheel angle, and speed are just a few of the information that is shared among the vehicles, and multiple times per second, and so that each vehicle is aware of the nearby vehicles. The one of the important metric is the relative position of vehicles compared to each other. However, not all of the vehicles with the deployment of the system will not support the DSRC. Yes, some of them, the new vehicles will be coming with this technology, but not the current one or the old cars. And although this device can be installed into current cars, some of the vehicles that are traveling on the roads will still not support these systems. So the detection of those cars would be a problem. Also, the position information is depend on the GPS signals, the global positioning systems. And if there is a problem with the GPS information, then the shared location information cannot be shared among the vehicles because the GPS is not giving the correct information, and it can cause some other problems. And the last problem that we want to investigate is the privacy. The information shared by vehicles, among others, should be anonymized because of to maximize the privacy of the users. However, is it really anonymized? So, is there a way to extract the driver information from the shared information using these vehicle communication systems? So, to understand this, and answer these questions. In this thesis, we have 3 individual projects. In the first one, we investigate the GPS jammers on roads and develop techniques to detect and identify them. In the second one, we investigate the driver specificity of the vehicle data. So actually the question that we want to answer is, what can reveal the driver identity? And in the last one, we investigate the traffic conditions, like detection of all vehicles that are traveling, that are using the DSRC or not DSRC, current ones, the future cars, like all of the cars using vision techniques. Let me talk about some of the related works with the GPS jammer detection. There are works with using handheld devices that can be used manually and detect GPS jammers, especially in the parking lots. But for the road case scenarios, that for the traveling vehicles, they are not good enough. And there are some location-based systems. Oh, we get the call from Fan.
Hello.
Hello, Fan.
Hey, Gorkem, thanks speaking. Sorry that I'm back. It's ended up being a drill and for 15 minutes. And my apologies for this unpredictable event.
No problem, Fan. This is Marco. Right. We just got started. I don't think you missed much.
Yeah, I was talking about the related works, Fan. That you all know about it. But anyway, for the GPS jammer detection, the second work is using the location-based systems to pinpoint the location of the jammer. However, again, for especially the dense traffic, they won't work to identify the jammer case. For the driver identity revealers, there are some works that are using the smart key fobs or the personal mobile devices, and or the traffic information, for example, the starting by knowing the starting position and the end position. There are works to identify the driver identity. And the last one is about the traffic estimation methods. There are works that are using the stable traffic cameras and using background subtraction techniques that are detecting the locations of the vehicles and counting them, and with this way estimating vehicles. Let me start with the first project that we did for this thesis. And this is the detection of on-road vehicles emanating GPS interference. And it's a collaborative work among Rutgers, Stevens, University of South Carolina, and Colorado Denver. In this one, let me start with the basic scenario of the GPS. It's the short term for global positioning system, and is widely used in navigation and transportation system. In addition to personal usage, it can be used in supply and shipping chains as well. And since these infrastructures depends heavily on the GPS, any disruption in the GPS signal can cause severe damage into industry. But due to approximately 20,000 kilometer distance to the transmitting satellites of GPS satellites to the ground receivers in the world, the received signal strength is extremely low. Therefore, these GPS signals can easily be masked by other transmissions, either from some malfunctioning electronic equipments, or the particular concern is actually the jammers. The jammers are easy to use, and some of them, as you can see here, can easily be plugged into the cigarette lighter of the vehicle for power and disrupt the GPS traffic in the radius of tens of meters. So these devices are mainly used by the drivers to gain location privacy. So some truck drivers, for example, are using these devices to prevent their employees to track their locations. And these devices can also be used by car thieves, because most of the recent cars are come with the built-in GPS receivers, and if you want to steal the car, first you need to disrupt the GPS traffic of that vehicle. So let me talk about one of the real-world problems that has been happened actually in 2010, I think. In airfields, in order to land in securely and successfully, the ground GPS receivers are placed in the airport. And with this way, the autopilot controlled landing mechanism can be enabled by using the ground GPS receivers. However, in 2010, at Newark airport, ground GPS receivers did not work for a few minutes repeatedly over a couple of months. And within these periods, the pilots could not use the autopilot to land in, and they have to land in manual, and it caused serious security problems for them. And it took 3 months for FCC to locate down the problem, which is actually a truck driver using a cheap GPS jammer in the I-95. You can see how close the road to the ground GPS receiver, and when the truck is passing nearby, the GPS receiver is interfering with the GPS jammer frequency, and did not work for a few minutes. And since it's a real-world threat, and it took 3 months for FCC to locate down the problem, I will talk about how they solve it. Then the researchers started paying more attention to this problem. How did they detect about the jammer? They used on this overpass a spectrum analyzer and scanned the GPS traffic. And when they find a normal signal that's transmitting at these position, by using cameras, they detected the place of the vehicles, and followed them by using patrol vehicles, and stopped each individual car to make sure that they are not carrying the GPS jammer. However, one of them did, and actually was caught. In United States, the usage and selling of these devices are illegal. You cannot buy these devices. However, you can get them online with cheaply starting from $50. There are some solutions that are designed to detect these jammers. The first one, as I said earlier, handheld devices. They work only in static scenarios. For a moving vehicle, they don't work, and they can use manually for a short time. The second method is the standard wireless localization techniques. They are not sufficient to pinpoint a vehicle, especially in a dense vehicle, because the vehicles are moving with a group of vehicles, and it's really hard to identify which vehicle it is. So what we propose, what is needed, we need a detection and identification system that should be automated, like it should be working with minimal human interaction, with high accuracy, because if this system would be used by enforcement agents, it needs to work with high accuracy, and of course it should be costed with a minimum amount of money for wide employment. Let me talk about what we are doing in this system. Let's say there's a jammer on the road. Since the spectrum for the GPS signal, which is 1.5 gigahertz approximately, is reserved for the L1 frequency, any transmission at this band is illegal. So we are using a threshold algorithm, energy detection method, with if the signal exceeds a threshold, then there should be a transmission at this frequency, which is illegal, and we can detect the existence of the jammer with this way. However, detecting is not the problem, because there could be several vehicles at the time of the detection. Then the second problem would be the identification challenge. Before I go through that, we are using the monitoring points with traffic cameras. We record the plates of the vehicles such that we know that one of them should be the jammer, and I will talk about the identification challenge in a minute. And we are also using mobile phones for detecting vehicles, because they're already more than enough on roads, so if there is a way to detect jammers by using them, it would be really efficient. But let me talk about some of the challenges before. Because of the strong attenuation of the metal bodies of vehicles and the Doppler shift, because the vehicles are moving on the road, it's really hard to detect a single vehicle to say that this car should be the jammer. And also, the availability of GPS performance metrics are limited for mobile phones.
What do you mean by the Doppler shift?
Doppler shift, because the signal is
How fast is a car moving?
Well, if the car is not moving, then locating that signal would be easy.
But what do you mean then by the Doppler shift making it hard for you?
Because if the car is moving, then the movement of the signal will change with the Doppler. So
Yeah, but most transceivers are already able to do frequency lock and frequency tracking, and the Doppler shift is going to be comparable at 50 miles per hour to the normal frequency.
true. First of all, we don't know if the car is using the same speed, stable speed. They can change their speeds. Secondly, multiple cars can be traveling.
You've proven that actually Doppler shift is a real problem? Or is this, I mean,
It's one of the problems.
One of the problems. But, I mean, wireless devices, such as my cell phone, were designed to have transceivers that can handle me driving around at 50, 60, 70 miles per hour.
True.
Again, that's frequency tracking. It's in here.
True.
So is that really a problem, or is that?
This is one of the challenges in the detection of the signal. A general challenge that we found another way to solve this problem.
Yeah, but I understand, I've read your papers, that you have another way of getting around the detection problem. I'm just not necessarily believing that Doppler is a justified problem. You got other problems with the jammer and stuff, but Doppler itself, I just feel like that was something you wanted to say.
Yeah, well, I mean, if you want to push on this, you could do a back of the envelope, so.
No, but the back of the...
No, I know,
back
speed of
the
light is
envelope.
1 foot per nanosecond, so if you're moving at 50 miles per hour, what fraction
Yeah.
of the wave actually moves?
At 15 and 1.5 gigahertz, I don't know, without doing the numbers formally. Probably like,
Well,
how
no,
many hertz?
one
It's not that
nano,
much.
if the wavelength is, what, a couple centimeters? So you moved a couple centimeters in 1 nanosecond,
Yeah.
billionth of a
I
second.
think it's just,
so.
you know,
How far in one, at 50 miles per hour? How far did you
This is his scientific exam, so what do you think? I mean, you said Doppler. Support it. How much Doppler is it really? And is it really a problem? Given that this thing can handle the same Doppler.
Yeah, they're probably using 900 megahertz and we're using 1.5 gigahertz, so I think it would be similar, the effect.
Alright, let's move on.
Well, I mean, you do have that point. So what is irregular about the radio environment? That second bullet there, it says radio propagation is irregular. I mean, it's not just Doppler, there's other things that are irregular.
I
So
mean,
what-
if you meant by Doppler the fact that the car itself is going to be out of the vision of your camera or something, that might be different. But if you're talking about the actual GPS jamming signal is undergoing Doppler shift, I don't really get what that means.
Well, don't think it in the GPS sense. If we're transmitting any signal with a moving source, compared to transmitting the same signal with a stable source. So with a stable source, by using, for example, by using 2 of the antennas, 2 different monitoring places, I can actually pinpoint it. If it's the moving case, then the position, the signal may not be moving with the same speed of the vehicle. Like it can go a little bit in the front or in the back. With the multipath effects are another problem in this case, because there will be multiple vehicles that are moving and the signal will be coming through not always the direct line of sight. So it could also create some problems.
So this is now about localizing
Yeah.
that jammer.
Yes.
Alright, I think there's a lot of propagation literature about relating Doppler and complexity of the multipath environment. The point is that, yeah, that just increases your error bar on your localization. Alright, go on.
And let me talk about what we are doing. We are using multiple monitoring points. Let's say by using one monitoring point, we detect existence of the jammer. And let's say there are 6 vehicles at the weave of the camera at the time of the detection. So one of them is the jammer, but we don't know which one. By using another monitoring point, probably a few miles apart from the first one, we expect to get the similar effect of the jammer in the same monitoring point. However, the sets of vehicles would be different if we assume the distance between the multiple monitoring points is increasing, then the likelihood of having more than one common vehicles in the sets of candidate vehicles would be really small. And this is our approach by using 2 monitoring points and intersecting the sets of candidate vehicles of 2 of them. Let me talk about what we are doing in detail. We have the energy-based jamming detection component, and in the first one we have the wireless receiver, which is continuously monitoring the GPS L1 band. In the second one, interference detector, we use a simple threshold algorithm if the signal is exceeding a threshold or not. And with the signal analyzer, if the signal is exceeding the threshold, we can further analyze the signal and compare it with some known jammer signals. And with this way, if it matches, then we can notify the some enforcement agency to take necessary actions. And let me talk how we place them on real roads. We choose a suburban highway in Princeton area, the monitoring point 1 and monitoring point 2, and the distance between them is 3 miles. And in each monitoring point, we are using a radio peripheral device, the USRP N210, with a laptop and GNU radio scripts. And we are choosing the locations based on the availability of an overpass for the camera placement and a safe place for us to park our car for the monitoring point. And actually, Why do we need to park our car so close to the road? Because we propose to use the directional antenna that is facing perpendicular to the road to have minimum set of candidate cars. Because we could be placing our antenna over here as well. But however, then there would be many more vehicles that could be one of the candidate cars. But instead we want to minimize it, and we decided to use the camera that's facing this way. And also, when the jammer is moving, theoretically we expect the signal should be picked at the closest position to the monitoring point, that is on the straight line. However, due to some multipath effect or some speeding, it may not be always true. With this way, we decided, instead of using a single line, we decided to create a detection area such that when the signal is picked and detected by the monitoring point, the car should be somewhere in this area. And the question becomes how to decide the size of this area. And with this one, to answer this one, we made some real-world experiments. You can see the 0 is the position of the monitoring point, and -20 of the left side, and 20 is the right side. And we recorded the position of the vehicle that is transmitting the signal when the time is detected. And you can see the locations are being shown by the blue circles. And we created the area just to intersect, just to cover all of these points. And with this way, we have the detection zone. So what this enables us to make sure that the car should be in this area at the time of the detection by using real-world experiments. And let me go through with some of the performance of our algorithm.
Pause for a second.
Sure.
So you have a vehicle driving through that's emitting some type of signal.
Yes.
All right, you didn't really describe that setup. All right, so what signal is being emitted?
Since it is illegal to transmit at this frequency, which we are not transmitting at that frequency, we are transmitting at 900 megahertz, which is the GPS band, which is the unlicensed band, which is free to use by any user.
All right, but now, a little rewind a little bit. A while ago, you tried to say that the Doppler at 900 was different than
Should
the
be
Doppler
similar.
at 1500.
I tried to say should be similar.
All right. All right.
But, let me talk about some of the metrics that we are using to evaluate our system. The first one is the detection rate, DR. What is it? The percentage of the passes during which our algorithm detects only one vehicle, which is actually the culprit, which is the transmitting vehicle. And the second metric we use is the false positive. When a vehicle that does not likely to transmit the signal, however, our system says this should be the jammer. And using total of 20 passes, our system always decides that the car is in the set of the candidate vehicles, so we have no false positive. However, you can see that the y-axis is showing the number of candidate cars. For most of the time, there are more than one vehicle in the set of candidate cars. In the monitoring point one, in 13 out of 20 cases, there is only one vehicle, which is our vehicle, so we have 65% performance, detection accuracy and identification accuracy. In the monitoring point two, we have lower results, about 35%. I will talk about why this is the case for monitoring point two in the next slides. As I said earlier, we wanted to combine the information that's coming from both monitoring points by intersecting the candidate sets at monitoring point 1 and monitoring point 2. This is the footage from the monitoring point 1. As you can see, the road is only 2 lanes and 2 lanes on the other side. However, on the monitoring point 2, you can see that our monitoring point can actually detect lots of vehicles. That's why we have more number of candidate cars in the monitoring point 2. But combining these information, the sets of vehicles, candidate vehicles in 2 of them, this resulted in a single detected vehicle, which is the culprit, which is transmitting at this frequency, and correct identification of our transmitted vehicle in all cases. So we we can claim we have 100% accuracy. After identifying these vehicles, we wanted to observe if these jammers, this time jammers, not the cellular, not 900 megahertz, however 1.5 gigahertz transmitting vehicles are actually existed on the road, and we did some passive roadside monitoring. So 5 locations are chosen in 2 states, and we did 200 hours of passive monitoring. We chose a major highway, one of the busiest toll roads, and an urban road. So we parked our car just next to the highway and started listening on the GPS frequency. And 2 suspicious interference incidents are detected. We do not claim that these are actually jammers. They might be. However, we did not follow them because we did not have the right or the ability to follow them and to make sure that they are actually carrying the jammer. However, it still proves that the interference exists at the L1 frequency, which should not be happening because this band is illegal to transmit. And any spike, any transmission on this band can cause problems with, as you saw in the example of the Newark airport. The last part that I want to talk about with the first project is the mobile detectors. So since there are multiple mobile phones that are already available on the roads, if there's a way to use them, then it would really make our job easier. So we are using the SNR values. What is SNR? Is the signal to noise ratio, which represents the signal strength of the GPS signals that is received by the mobile phones. And we created a 2-stage algorithm. In the first one, we used Android API to get the current SNR values for a specific location. And then we created an SNR profile of a road, like a sample road, by matching SNR with the GPS position. You can see in this road, the 0 represents the Bush campus and 15 represents the WINLAB. So we created the SNR profile from Bush campus to WINLAB. And you can see that it's usually in the around of 50 dB, the GPS SNR. However, there are some drops. And actually a big drop is happening when we investigate the location. This is just after the College Avenue campus. And there is this underpass that we are traveling about 20 to 25 seconds. And in this period, you can see there is a huge drop in the SNR. And there are some other drops which we suspect that they're happening because of some billboards, some big billboards on the road. And in the second stage of our algorithm, we detect these anomalies. We compare the current reading of the mobile detectors, and if the current reading of the SNR is lower than the expected SNR that we created using the profiling stage, then there should be an interference at the L1 frequency such that the central office could be notified. And let me conclude the first project by we presented a low-cost jammer identification system that can be deployed in roadways and to automatically detect and identify these jammers. And we are using monitoring stations with cameras and directional antennas and mobile detectors. And our mobile detector can detect the interfering signals based on the measurements that are already available in most GPS receivers, so it's possible to detect jammers via crowdsourcing. So before I start the second project, is there a question about this one? Okay, then let me go quickly. The second one is the pre-trip driver identification from the in-vehicle data. This time we collaborate with Southern California University and General Motors. Our motivation is cars can be shared either among family members or among colleagues, like the carpooling cases. The goal of this project is identify different drivers within a group based on their driving behaviors. And there are some current solutions as well. The first... Hello.
Hello, Gorkem, my apologies. Something wrong with the microphone line. Yeah.
Okay, welcome back. The first current solution is the usage of smart key fob. Usually the vehicles are coming with 2 key fobs per vehicle, and if each driver is using their own key fob, then it should be a way to identify the driver. However, this is usually not the case. Some families can be shared their key fobs and use the second one as a backup. And the second one is usage of a personal smartphone. It works only if the driver keeps the phone with himself while driving. For example, if he doesn't carry the phone, it will not work. Or if he places the phone at another position in the car, the system may not work. And in the last one, by using the complete trip information, which can take minutes and even hours, because they are using the start point and the end point to decide on who the driver is. It may not be robust, because sometimes they can just change the driver and still drive the same road. So we need a system that should be automated. This time we need a quick system, because we don't want to learn who the driver is at the end of the trip. So probably in the first few minutes, if you can learn about the driver, that would be a useful app, with high accuracy and of course at a low cost. This time the challenges are the similar behaviors of different drivers. In most cases, the parents are teaching their kids how to drive, so their driving behaviors could be the same, could be similar at least, and the style of driving for different moods and days can change. For example, if you have an early meeting or like a defense presentation that you might need to drive a little bit faster, but it could be a little bit different than your usual behavior, or sometimes in the weekend, for example, if you're relaxed, then you can just change your driving style, so it could be another challenge. And detecting strangers could be tricky as well, as the last challenge. So what we propose is we propose to use only sequential events that are happening in the beginning to use the minimum time to detect who the driver is, and also minimum data. And we are using their order. For example, if a driver is using the fasten the seat belt before changing gear or not, or he uses seat belt after changing gear. And the timings are also crucial, so we are also using the timings of these events. So how much time it takes, for example, between the changing gear and releasing brake. So we call these events pre-trip events, because they happen usually in the beginning of the trip. So we have 3 components that I will be talking individually. Let me start with the first one, and by defining the pre-trip fields. We are using the door open as the first event, and the door close. The ignition switch usage is the time when you run the engine, and the seatbelt fastening time, like shift usage, is the changing the gear and the release brake. So we are concentrating only on these events to understand who the driver is. So we create the features by using the time differences between these events. We say that the door open should be the origin event, that should be happening in the time equal to 0, and then calculate the time difference between, for example, the door close to door open, to ignition switch to door close. So individually time difference events, and we create our features for each driver. And after this, we use a learning algorithm that is a support vector machine, SVM, with a linear function that is supported by MATLAB. But why we use this? Because it's computationally lightweight and suitable for real-time driver differentiation on mobile devices. Let me talk to you about the data set that we use to evaluate our system. 3 different data sets. The first one is the university Mailvan trucks that are traveling across the university campus, which is happening in the South California. The second one is collected by GM employees over the summer that are traveling in the GM campus. And the last one is collected by 2 sets of households that are the members of WINLAB, actually. You can see the Mailvan test environment in here in the downtown Los Angeles area. Total of 5 Mailvan has been used, and we collect data over 3 weeks. Total of 480 trips. We call the GM data set as the control test environment. Each driver, each intern actually, using a Cadillac with total of 16 drivers and 160 traces. And in the household settings, in the first one we are using a husband and wife we give them the car for personal usage. They can drive, they can mimic their everyday usage for their car. They just replace their car with the car that we gave them, which is a GM vehicle. And the husband is drive 29 times, and the wife driven the car for 37 times. So since they similarly drive the car in the numbers wise, our main purpose to distinguish both drivers accurately. However, in the household 2 mother and daughter case, mother is the primary driver who is mostly driving the case, 33 drives, and daughter just drives the car over the weekends, for example 3 drives. And with this way we wanted to mimic the detecting the stranger case that we proposed in the challenge, one of the challenges. And let me go through with some of the results. Control test is the GM case that we have, and Mailvan is the United Southern California University case. You can see in the x-axis is the time. So within less than 20 seconds we are getting these results, and in the y-axis we have the accuracy. So different color represents the different number of drivers. For example, 4 drivers, 8 drivers, and up to 16 drivers. We have about 90% identification accuracy by using the data of less than the first 20 seconds. So our algorithm, at the end of the 20 seconds, with 90%, can detect who the driver is. For the Mailvan case, we have less number of drivers because there are only a limited number of drivers. We have up to 5 drivers, and we have a little bit higher results. I think the 92% was the actual number. Again, in less than 20 seconds. These are the critical results of this section. However, for the household setting, we don't get this accuracy in such a short time because of the daily routine. Sometimes they do quick trips, but sometimes they just get on the vehicle and make some phone calls. So it takes some time. It takes even minutes to start the vehicle. However, our accuracy is still being shown here. The driver number 2 is identified correctly by 93% for all the trips, and driver number 1 is identified with the 79%. So in the average, we have about 85% driver identification accuracy. For the driver number, household number 2, which is the mother and daughter case, mother is almost always identified correctly, like I think 32 out of 33 cases. But however, the daughter could be identified correctly by 2 out of 3 cases. That's why we have the low number, because the daughter only drove the car for 3 times.
Wait, so go back. So that result is just because you only had 3 sample points?
Exactly.
So it's not really...
Because mother is the primary driver.
Yeah.
Right,
So
so
she,
you shouldn't be using percentage for that.
true,
You need to,
yeah.
somewhere else.
That's why I wanted to say 2 and 1. That's why we got 67%.
Well, even then the mother's results too are a little bit...
In only one case, mother is off. I think 2
Right,
to
but
2.
if you had just randomly guessed the mother every time or something, I don't know.
Yeah, it's almost the
It's
same.
almost, okay. Just don't have enough data.
In this one, we just show how similar of the husband and wife is driving. This is just a detail, but let me summarize it quickly. Husband is driving from first 15 trips, in our case 1 to 15, and we actually seen, and y-axis is the distance of the similarity. If it's high, then it's really different behaviors. If it's low, then it's almost a similar behavior. And you can see that 6, 7, 8, they're all from husband, and the similarity matrix is really small, so which is expected. However, for some cases, like you see here, 14 is coming from the husband and 26 is coming from the wife, and the similarity is almost, this distance is really small, so they behave really similarly. So even in these cases, in these scenarios, still getting 85% accuracy is our main result for the household cases. And let me conclude it. We present a no-cost driver ID identification system. That is one of the most important results that we have to automatically identify the drivers. We are using the pre-trip field extraction and clustering algorithms. And we are using OBD2 dongle to collect the information from the GM. And this is a custom dongle because in most of the cars you can still access the in-vehicle data. However, it's not detailed. You can only access the speed, you can access the RPM values, or like some climate, the temperature inside the car. However, by using our custom dongle, we have the door open time, door close time, even for some models, the seat model, the seat position. So by using this specialized dongle, thanks to FAN, we have access more information for GM vehicles only. That's why we aim for the GM vehicles.
So when you say customized dongle, I mean, is it the software in the dongle that's customized? Or
It's
what's the
both
customized
software
part?
and the hardware actually.
So why did you need hardware?
Hardware, that's their specific dongle is not working, for example, with my Nissan Altima. When I tried it, I cannot read anything. The data is encrypted. And by using the software, we can actually decrypt it and
Well, right, that's what I meant.
You don't need customized hardware, but for safety purposes, GM created customized hardware that allowed only limited access to the proprietary data.
They don't follow the bus
put-
standard
since-
themselves.
No, since you can potentially affect the brakes and cause cars to crash with by having software bugs, there was some special hardware that filtered out certain things.
Yeah, it's customized for some very special functionality, and mainly reason is safety and security concern. And but unfortunately, that we couldn't really talk much in the public forum on that situation, given we all understand the implication of the security.
Okay.
So this is an interesting behavior-based user identification. Based upon my own family, isn't it the seat position alone will be the deterministic factor
True.
in determining who is driving?
true. And also there are some weight sensors in some models. But however, we
My
do not
family
have
probably
access.
too, but I'm not sure that's true of every family.
Well, I just, so yeah, that's coming from the question among, you have a vector features, right?
True.
Did you actually study which one carries the most weight in?
We did. Actually, we did.
Go back here, right?
I do not have the results here, but in my thesis, I compared each of the features one by one, and I remembered that the third feature that we use which is the seatbelt fastening time, was the
What time?
seatbelt fastening. Because some users fasten the seatbelt before changing the gear, and some of them, after they start driving, they change it.
That's the most determining
The most
factor.
determinant one, yes.
Interesting.
And even some users do not use the seatbelt fastening at all.
That's not.
That's not safe, but all the others are mandatory. But fastening seatbelt is not.
So I think seat position would be very valuable in this data set. It was not included. It's only relatively.
This is all temporal.
It's only
sequence.
it's only relatively new cars that have the appropriate sensor for that. On older cars where you manually adjust the car, there's no idea where your seat position is.
And some people put the gear first.
The order, yeah.
How many times do you yell at your kids, sit down, put your seatbelt on, or I'm
And
driving?
And
And then finally you
this is
shift it,
driver
then they
identification.
freak out and they
Okay,
quit.
interesting. That's good to know.
Yeah, especially parking lot, even sometimes I do. First, I just back up, I start with the D mode, then use my seat.
Seatbelt?
Yeah.
Oh, okay. So what is the most, for this study, right? If you learn one lesson, let's say intellectual lesson from it, what is it?
Well, first of all, for the professional drivers, they do everything automatically. Like you saw that it's like in 20 seconds, they're almost always just get on, start driving that time. However, for household cases, it takes some minutes. Because especially when I talk to Noreen, who is one of the members of the household number 2, she sometimes get on the car, door open, door closed, and make phone calls before even starting.
Right, so these are like user behavior
Exactly.
lessons. So how about from your methodology point of view, what is the biggest lesson that you have learned? Let's say if you're going to conduct a similar study on a completely different system, what can be applied there?
We use different clustering algorithms. We started with K-means. We also use hierarchical clustering, and we try to compare all of them in the paper as well. And if we know the total number of driver, we can always use k-means and everything is easy. However, if we don't know how many drivers are actually driving the car, for example, today you and your husband are driving, however, in 5 years your kids will start this car and will start driving the car, then a new driver behavior will completely change the system for us.
Okay, that's a reasonable lesson. All right, let's move on.
And finally, let me talk about the last part of the thesis, which is the real-time traffic estimation at Vehicular edge nodes. This is another collaborative project, surprisingly, between the Southern California, Rutgers, and General Motors again. Our motivation is to learn the relative position of vehicles. For the DSRC systems, the GPS information is shared. However, as I said earlier, most cars, or actually let me say some cars, will not support the DSRC, at least in the initially. And our goal is the real-time vehicle detection and tracking. And for this goal, we decided to create a sample app that estimates traffic using the vehicle detection and tracking. So the current solutions are using the traffic cameras, and as of 2015, there are over just a little bit 4,000 traffic surveillance cameras in US roads. So compared to all of the intersections and all of the highways, this number is really small. So if you want to learn about the traffic estimation, traffic results for a sampled road, the likelihood of having a traffic camera on that specific road at that specific intersection is really small. So not all roads are covered with surveillance cameras. And some navigation apps, such as the Waze or Google Maps, shows the approximate traffic on the road as well. However, they're using the reports, the reported GPS data from users to estimate the speed of them, and they do not calculate speed for every vehicle because they do not have access to this information from all drivers. And they might be using outliers, for example, for a speed driver or for a really old driver, and they might result with the outlier, so the results might not be accurate enough. So we need an automated, real-time, with higher accuracy and widely deployed system. So what we propose is we propose to use front-facing cameras that can be placed in the vehicle to record the traffic, and then using a real-time object detection technique, which is the vehicle detection for our case, to detect vehicles in both directions, in both our direction and the opposite direction. And estimate the lane of travel for vehicles, for example, the estimate of the lane which is on the left side of this car or in the opposite side, and their speeds are some of the questions that we want to answer. So the first challenge is there are different traffic conditions. Some roads are just one lane in one direction and the other one in the other direction. Or in some ways, some roads, especially in the highways, there is this really big median strips. It's called these huge barriers, so they can block the view of you may not always see the complete vehicle that are traveling in the opposite side. And also, as I saw here, the wheel could be obstructed by some trucks, for example, in your left side. So you can only see the truck, but you cannot see the vehicles behind the truck. So these are the challenges that we realize. And in our system, we have three main sections: vehicle detection, vehicle tracking, and traffic estimation. So let me start with the object detection. We are using a real-time object detection method called YOLO. It's the acronym for You Only Look Once. And with this way, the image is split into grid cells, and in each grid cell, it predicts bounding boxes around objects and gives confidence scores for those boxes. And the higher the confidence score, the more likelihood of correct object detection. And in the current setup, it's designed to detect more than 20 different objects, including screens, chairs, people, animals, pedestrians, and vehicles. Actually, you can see in this picture, they just split it into grid cells and they decide, for example, this is a dog, this is a bicycle, and this is a car. However, it's mainly there are two steps in this object detection. The first one is the training. The network is trained with images of objects. So in their case, they train the network with 20 different objects. But for our case, we only worry about the vehicle. So we will train our network with the vehicle images. And they use 500 images of each object to train the network. And for the testing, the system can work on images and videos and can detect multiple objects in the image. So you can actually see this is the movie, one of the James Bond movie, and you can detect the person and the motorcycle at the same time. However, with the current setup, car detection performance is not great because they are using only 500 images to train the network. We use the sets from Washington University and Stanford University, the sets of images of vehicles from every angle. Like, I think 3,000 from Washington University and 5,000 from Stanford University, from different colors of vehicles, different models. And by using this sets, we train our network. And after this, we just go out and try to see the vehicle detection. As you can see, there are multiple vehicles can be detected on Route 1 actually. It's just outside of here. The second component is the vehicle tracking, how we track the vehicles. And we are using the SIFT features, skill invariant feature transform. That is implied, we are using the MATLAB version, and for each consecutive frame, we just decide on the SIFT features of the image and then compare with the next frame. So if there is a lot of features that is matched between the consecutive frames, then it means it should be coming from the same object.
So what do the green circles mean?
The features of the image.
So each circle is a different size and then there's a line in it?
Yes.
What
So,
is that?
for example, this one is being matched with this one. And each green circle is being matched by using this blue line. So it says that the feature here has been matched with this feature.
Okay, and so is this, what's the size mean and the line and the inside mean?
Size, if the size is big, then the likelihood is high.
Okay,
If you see, for example, for the
Okay, so
outside
the-
objects,
right, so the
It's-
radius of the circle is like the
The likelihood.
Okay.
yeah,
Alright. Does the line in the middle mean anything?
the line,
There's like a circle and then there's like a,
if, since these are taken with the consecutive frames, we expect to have parallel lines between the frames.
no, see, inside each circle,
Mhm.
there's a line
Oh.
going from the point to the outer, to the diameter. From the center to the
I
diameter.
see,
there's a
I
line.
just saw it, but
I don't know if that, is that meaningful or what?
even if it's meaningful, I don't know the answer.
Okay, alright, okay, alright.
Well, I think maybe it's built in with it's related to the SIFT algorithm. It's like the in one of the procedure in SIFT, there's an orientation assignment. So I think that the radius you mentioned may be related to the orientation about the SIFT features. There's a 128 dimension of each point, a feature vector, and there's a like major orientation of each vector. So that's like
The angle of that
yeah, the angle
line
might
is
related to
something-
the orientation, the direction.
Okay, well,
And we claim that if the number of match features between the consecutive frames is greater than a predetermined threshold, those two images belong to the same vehicle. This is the method that we say that this is the same vehicle, so we should not, for example, increase the count, and this is the way that we track each vehicle. And for the traffic estimation, the first goal is the vehicle counting. They estimate the number of unique vehicles that are traveling. We focus on the traveling in the opposite direction. However, for the same direction, we can also count the number of vehicles, but it's not really relevant because we would be seeing the same vehicle for a long time, so it will not give us meaningful result for the traffic estimation. And we use the detections from the vehicle detection module that I talked about. Then we extract the shift features between consecutive frames, and finally we match features to distinguish new vehicles. And in the second one, we try to estimate the lane of travel for the vehicles. In the same direction, it's easier because we can use the lane markers, and by detecting them, for each vehicle, lane estimation is possible. For example, if you look at this picture, we first detect the left line, which is the yellow line, and detect the right line. We say that this is the lane that we are actually traveling. However, for the opposite direction, since we cannot see most of the lane markers, this is not really easy. Instead, since we don't have access to lane markers, we propose to create, we call them pseudo lane markers by tracking the vehicles. And since each vehicle is usually moving parallel to each other, by tracking the vehicles, we can observe the movement of flow for each lane and then create the lane regions. And I will show the results of this technique in a minute. And finally, for the speed estimation, we use camera calibration, and we did the speed estimation for the consecutive frames of the vehicle video, estimate the relative distance change of the vehicle between these two frames, and convert back it into speed by using the well-known formula, where the distance, d is the distance change and t is the time difference between the frames. We use 3 representative roads. One is a campus road in Livingston campus with 2 lanes. The second one is the US 1 just outside, and in the third one is the major highway, which is actually in California. And I have the results for all of them individually. For the road 1 in the Livingston campus, we have made total of 10 tests, and all 25 traveling vehicles were counted correctly. So the counting accuracy for the 2-lane roads with 1 lane in each direction is 100%. For the Route 2 and Route 3, which are the highways with multi-lanes, and you can see that especially the left lane accuracy is really high. So we can count the vehicles that are traveling in the opposite side of the left lane with really high accuracy. However, when we go through the middle lane, the accuracy starts going down. And for the right lane, it goes down significantly. However, the overall, like if you take the average of all lanes, we still have over 75% even for the really heavy traffic. And we did the same test for the Route 3, which is a major highway in California, and we had similar results. For the left lane detection rate, we have over 89%, and for the worst case, which is right lane, which is just over the 73%. And the second result that I want to share is the lane estimation. You can see that we can estimate the vehicles that are actually traveling in the left lane with 94% in the Route 2. And for the Route 3, again with the 91%. And these are showing for 7% is actually identified as the middle lane, and with 2% we detected the vehicles that are actually traveling in the left lane. However, our algorithm says they're traveling in the right lane. So again, from left lane to middle lane and the right lane, the accuracy goes down. And the final result that I want to show is the speed estimation that we have. For the Route 1, the Livingston campus data, we have really good accuracy results for the relative speed. The relative speed is the speed difference between the vehicles. So we drive from two different vehicles with 25, for example, the mile per hour, and the relative speed becomes the 50 mile per hour. And our algorithm is estimating the speed as 50.5, so the accuracy is about 1%, and in the worst case we have about 4.85% speed estimation accuracy for the Route 1, which is again the campus road. However, when we go to highway, the speed estimation accuracy gets a little bit worse. For the Route 2, the Route 1 case in New Jersey, we have 8.5% speed estimation accuracy, and for the Route 3, which is the major highway, we have, in the worst case, 11.9% speed estimation
Can you
accuracy.
say again with the relative, that's the difference
Relative
between the
speed.
oncoming speed?
Yes, if I'm driving at
Okay.
25, and if
Yeah.
the other car is 25, then
Okay.
50.
So then what's the estimated? Is that the estimated relative speed? Or
No,
that's just the
estimated speed of
estimated-
our algorithm, by using our algorithm.
The estimated speed of the other car?
No, the relative speed.
The estimated relative speed?
Yes.
Okay. Oh, you have a bug in your table on Route 1, then. The last row. See, it says relative
Yes.
speed 95, estimated 81?
Yes, yes.
Okay.
That's interesting.
Well, no, I was trying to figure out what they were, because I saw that, I was like, okay, all right.
And the conclusion of this project, we designed a real-time vehicle detection and tracking system.
So, out of curiosity, that bug you just found, is it in the paper?
I don't think so.
Is this the last chapter? Yeah, no, it's in the thesis.
It's in the thesis, okay.
Table 4.4. Yeah, you should fix that.
I should fix that, yeah. That's,
I think, I mean, it's just the error is wrong, if that's the right estimated speed.
Or there's
Or the
a,
estimated speed is wrong.
right,
You probably copied the fourth line.
probably.
yes.
Oh, yeah, it looks like a paste error, yeah,
Yeah.
yeah.
Okay.
Okay.
Okay. The proposed system can be used in any route to estimate the traffic, and it could be a nice addition to future DSRC systems. And let me conclude the dissertation with the summary of the three systems. First, we presented how to detect GPS jammers by using the monitoring points and the mobile devices. Then we investigated the driver differentiation technique, and finally we presented the traffic estimation system using the in-vehicle data. And here the published papers that I have. And before finishing the presentation, I want to thank to some people, including but not limited to, starting with Marco. Thank you very much for everything, and for my dear committee members. Then some of the professors that are really helped me a lot with the projects that during this 5.5 years. And then special thanks to Shubham, Hang and John that are my main contributors for the projects, and all of our group, all Marco's students, both current one and the old ones, and special thanks to Jan. He is right now a professor in Binghamton University, and that's all in my presentation. If you have any questions, I'm glad to answer them.
Thank you. All right, are there any more questions?
Questions from
From the audience?
For the GPS data and the speed estimation, actually, as far as I know, there is a error in the GPS speed or was it
GPS based.
Yeah, okay. There can be also GPS based estimation.
True.
error, right?
If we have access to OBD2 based speed, then it would be more robust. But for the data set, we only had the GPS based speeds.
Even that also has a small error, as far as I know, limited to some value.
I agree, but the good thing is we are always doing the experiments in the open environment. So there is no high buildings, so GPS performance should be really high for that case.
Okay, then we go into closed session.
Yep.
And can someone let Jake know about it, because we need to stop the transmission.
Okay.
streaming this event?
Yeah, I just told them, so probably in 30 seconds they should be.
Okay, let's go out with it.
So what's the next step?
I'm planning to go back to Turkey. I'm from Turkey,
Okay,
and
very good.
right now I have 3 offers, and in 2 of them I passed the first interview.
For you.